Welcome to the 23rd episode in the mathsonlinetuition.com videos, where we're continuing with the C2 book. We're on chapter 7 entitled Geometric Sequences and Series. Here are the 5 aims and objectives of this chapter. Recognize the geometrical sequence and state the common ratio. Calculate the nth term of a geometric sequence. Find the sum of a geometric series. Solve problems involving growth and decay. Find the sum to infinity of convergent geometric series. So 7.1, the following sequences are called geometric sequences. To get from one term to the next, we multiply by the same number each time. This number is called the common ratio R. So if you recall, when we were doing arithmetic sequences, we had a common difference, okay, which we entitled D. Here we call it the common ratio. So you see a 1, 2, 4, 8, 16, and you can notice that the number is doubling, so the number preceding it will always be half of it. So 1 multiplied by 2, 2 multiplied by 2, 4 multiplied by 2, and so forth and so on. And then here you can see, okay, it's divided by 4. Okay, so in this particular case it will be multiplied by a quarter, and so on and so forth. So you can see already from the offset that in the geometric sequences we're dealing more with perhaps multiplication, as opposed to with the arithmetic sequences we were dealing with addition and subtraction. So here are some examples, okay, for you to appreciate what the common ratio is, in a way of finding out what the common ratio is by essentially taking two opposing numbers, okay, numbers alongside one another, and dividing them, and you will get the figure, the common ratio R. So 7.2, you can define a geometric sequence using the first term A and the common ratio R. So this is telling you that you can find the nth term, or any n term in the sequence if you utilize the given information which we need, that is the common ratio and the first term. The first term, because this is where the sequence begins, and the ratio obviously to give us that the mapping onto into how to progress onto the term number n, or the nth term. And so you can see that we do this by, or first of all, we have a first term in this particular question, which is 3, and this particular one here, which is 40. And then, as we showed with the early calculations, we can, if we divide 6 by 3, or 12 by 6, and 24 by 12, we can start to see that there's a common common ratio of 2. So here it's multiplied by 2. Okay, so we can appreciate this, and therefore we can say that the nth term is going to be 3, the first term, multiplied by multiplied by 2, which is the ratio term, to the power of n minus 1. And the reason why it's n minus 1, okay, is because of the fact that A, which is 3 in this particular situation, okay, is a term, is the first term. Okay, so we take away n to the minus 1, alright, to offset the fact that we already have the first term here in this particular equation. And the same thing for this question here. You can see that we've got 40 as the first term. Okay, that's brilliant. And then the ratio, if we divide 20 by 40, is going to be minus 20 by 40 is going to be minus a half. Okay, so we've got the first term 40, and we've got the ratio minus a half. Okay, but then if we want to find the nth term, okay, recall again that is going to be minus that we're going to have the following, that if we want the nth term, we already have 40, which is the first term, so that's a term. So our ratio minus a half is to the power of n minus 1, to offset the fact that we already have the first term here. Okay. So example 3, a very simple example. Find the common ratio, the first term and the 10th term. So everything that we've done before, and you can do in your own time. Some more examples here just to test your ability and your understanding. 7.3, you can use geometric sequences to solve problems involving growth and decay, e.g. interest rates, population growth and decline. So a lot of the time people ask questions like, when is maths ever going to be applicable in my life? And when you're at a young age doing A-level and GCSE, of course, you can't appreciate this because most of your life has been within the academic sphere. You've been in school. But this particular example here, this particular subsection gives you an insight into perhaps some of the dealings that people in the financial world utilize. It's very simple, it's very basic, but a more advanced level of this particular subsection is used in real life to figure out mortgage rates, to figure out interest rates when it comes to banks and other such dealings. So this is an example of how a mathematical question can be used, okay, to resolve a real life scenario. So Andy invests £8 at a rate of interest 4% per annum. After 5 years, it will be worth 10,000. How much to the nearest penny will it be worth after 10 years? So just terminology check. Annum here is annually. That's every year. Okay. Again, 5 years, it will be worth 10,000. So you know how much Andy has in the bank. To the nearest penny. Okay. How much will it be worth after 10 years? So this is running you through an appreciation of how to work out this question. After 1 year, it will be A multiplied by 1.04. Why 1.04? Well, here you can see that you have 100% plus 4%. 100% represents the value Andy already has in the bank account, which is £8. And the 4%, which is the 4% interest per annum, okay, is represented by the decimal 0.04. Okay, this is just decimal representation. So after 2 years, you can see that it will be A multiplied by 1.04. So this is the beginning of year 2, so the end of year 1. Okay, this is what it will be worth, A multiplied by 1.04. Now at the end of year 1, or really beginning of year 2 to be more accurate here, it will be then that value will be worth something multiplied by 1.04. Okay, so let's just write this out so that you can get an appreciation of what I mean. Let's use some simple digits. Okay, so we've got Andy has £8. Now he, after the first year, okay, is going to have a value of, let's say, X pounds, right? Now X pounds, okay, after year 2 is going to be multiplied by, again, 1.04. So we're going to have Y pounds. Now Y pounds, again, is going to be multiplied by 1.04, okay, which is going to be equal to, again, we say Z pounds. Now Z pounds in actuality, all that means is A pounds multiplied by 1.04 multiplied by 1.04 multiplied by 1.04. Okay, and this is after year 3. So let's just make that clear here. So this is year 1, this is year 2, this is year 3. Okay, and so in another way of representing this is A multiplied by 1.04 N, okay, on year N. And so you can see that they've done this here. So they've utilized that. So they say A pounds multiplied by 1.045, okay, is going to be worth 10,000. We already said that. So now all it's done is simple rearranging, and then through that we get this. So the initial investment of Andy, okay, which was A, is equal to £8,219.27. So after 10 years, the investment is worth A times 1.04 to the power of 10. So I hope you're appreciating here that years is the number of years that they want you to look into, is the N value here. And so the same thing happens, okay, whereby you have this particular value, alright, and then it carries on as such. And again, with example 6 here, they are asking you for the first term in the geometric progression to exceed 1 million. So they want you to find that nth term where the geometric progression first exceeds, okay, 1 million. Now here you can see that we have the first term, which is 3, and then r, okay, again divide the terms together, you get 2, n minus 1. I've already explained why. Now we want the nth term. Now it's written it out for you more for you to view it in words. We want the nth term, okay, that is greater than 1 million. So they've input the equation here, the equation here, and then you can see that they have just simply rearranged. And in this particular situation now, you can see that n, okay, is a power. And if you recall, if we want to find this, or if we want to change n's position so that we can rearrange to make n the subject, okay, then we use logarithms. And giving you a handy reminder here of the logarithm rule, okay, or the law of powers as it's called. So utilizing the law of powers, we then have this summarized equation, okay, and then you can use a calculator to figure this one out, because I think a calculator is very much needed to work with this with logarithms. And then subsequently you get a number, 2 decimal places, and then again you rearrange the -1 to the other side, and you can see that you have 19.35, but 19.35 is not a whole number, okay, it does not represent a term, so we need to exceed that number to the nearest integer. So we get 20, and simply the answer is the 20th term is the first to exceed a million. Okay, I hope that explains the example, and some more examples for you to do. So 7.4, you need to be able to find the sum of a geometric series. Find the general term for the sum of the first n terms of the geometric series A, AR, AR2, ... ARN. Okay, so here now we're talking about the sum. So there was the sequence, and then there was this, and now there's the series. Okay, so here this is calculating the sum of the geometric series. If you remember, we calculated the sum of the arithmetic series previously, so now this is just dealing with the geometric form of a series, and adding them up together to find the sum. So here you can go through a simple proof of how they attain this series sum, and they've shown you perhaps 2 different ways of appreciating it. The difference between this and this is the fact that a negative sign has been changed in its positioning. So you have Rn minus 1 and R minus 1. Okay, if you want to change what's here in the brackets, this is another way of writing it: R minus Rn plus 1. Okay, and then you can also have R1 minus R, and so you can see that this negative here, can see that this negative here and this negative here would make a positive, okay, which will then give us a 1 minus R and 1 minus R. Okay, so there's no difference between the two, just a simple rearrangement of the negative term. And so you can find the sum of the following terms by simply putting them in. And then you have the first term, which is always evident, and the ratio, and you have the number of n terms. So all you need here is, so you need the A, the first term, you need the n number of terms, and then you need R ratio. Okay, simple calculation. And so for B, you can see the similar thing is done. So here are the terms that you have. So you have A here, which is 1024, and then you have N. So N has been you have R. So R is minus a half, and you have, and the nth term equals 1. Okay, so AR to n to the power of 1 equals 1. That's the nth term. So you can find out that there's 11 terms. Okay, and then essentially you need to then go on to calculate the sum of the series now that you have all the terms. Okay, these 3 terms, and you can find that this is 683. Again, very simple. Another worded question here for you to contemplate, but again, exactly the same as what we've done before. If you read through this question, so an investor invests £2,000 on January the 1st every year in a savings account that guarantees him 4% per annum for life. If interest is calculated on the 31st December each year, how much would be in his account at the end of the 10th year? Okay, so what does this mean? Let's just extract the data that we need. So an investor invests £2,000. So his initial investment, okay, in this case we could say A, is 2,000. Okay, and it guarantees him 4% per annum. So 4% per year per annum. And the reason why annum is used is because there's many types of years. There's a calendar year, there's an academic year, and so we have to kind of be careful as well with other cultures. There are the year is differing in China or in other places. Other continents use perhaps a different, more cultural, historical calendar. So annum is a good way for banks to convey what they term, what they deem a year. 4% per annum. If the interest is calculated on the 31st December, how much will you have at the end of 10th year? So n is 10. Okay, so just extracting this data. So in other words, this will be 0.04 in decimal place. Okay, and again, you just need to follow the procedure of what we've done before with our previous example, and you can look through this working out to see that it's exactly the same, just worded in a slightly different way. And again, you have more examples to do on your own. Here, example 11, find this particular result. So we have that the terms are 10. The first term is 3. You can see that the ratio is 2. Okay. Now, if we carry on opening this, we can see that if we expand it, it will look like such. Alright. And then essentially you can notice that there's a pattern here that everything is multiplied by 3, as it should be, and you have all the 2's collected together and the powers increase by a figure of 1, and so you end up with this particular equation, this particular formula, sorry, and as you can see it corroborates with our sum of the series. And so we have this answer that is 6,138. And you can work through the examples. 7.5. You need to be able to find the sum to infinity of a convergent geometric series. Okay, what does that mean? So no matter how many terms of this series you take, the sum never exceeds a certain number. We call this number the limit of the sum, or more often it's sum to infinity. Limits is something that you will heavily be involved in when you study mathematics or a numerical subject at university. It comes under a pure mathematics banner, whereas most of the stuff that you will do in A-levels comes under the applied mathematical banner. So you can appreciate by reading this text that we want to find the sum to infinity of a geometric series by utilizing this equation, this formula here. With this rule, if R, the ratio, is less than 1, and this absolute term, or the modulus here, okay, represents R between -1 and 1. Okay, so this R here represents the 1 and -1. Essentially, it's identical to this particular inequality here, and the hint is also referred to here. And here are some examples. So you take the first term, take the ratio, and you install it into the formula, and then you'll get the sum. Okay. Likewise here, the same thing is asked of you. And these examples, again, you can do in your own good time. And here we come on to the mixed examples, which signifies the end of the chapter. So just something very important for you to note: don't burden yourself too much with trying to get your head around limits at this point in time, because it's probably something new to you. But what you do have to appreciate in this chapter is the following. Please learn these formulas, this one, and this one. Please learn what terms are represented by each variable, a, r, and n, okay, how to solve them, okay, and also please gain a breadth of experience answering questions with a diverse form of questioning, i.e. a worded question, okay, or a question whereby a variable is missing and you have to resolve it. One good advice I can give is, in a question whereby you are provided, for example, with a, r, and n, and it's as simple as calculating the series. If you want to test your the sum, if you want to test yourself, look to the answer to figure out the sum, okay, but at the same time don't include one of the given variables. Try to rearrange the answer, okay, and then that way you can get experience trying to find different unknowns, and you can increase hopefully your ability to resolve the question regardless of what information you have, as long as it's sufficient, and that will deepen your knowledge and your understanding. So thank you very much for listening to this episode. We hope to see you again next time. Take care and goodbye.